Hello class, today we are going to talk about thermodynamics. This is tied to last week's states of matter and phase changes. We're going to talk a little bit more specifically about potential and kinetic energy, do a little bit of math, but talk more about what's happening in a system when we add heat or undergo a chemical reaction. So first we need a few definitions out of the way. First, what is the difference between thermal energy and temperature? So temperature, if we remember from last week on our heating curve, we looked at, we had our drawing that looked like this, where we had our plateaus and we had our positive slopes. So wherever we had a positive slope, that was a measure of kinetic energy, and that would give us a temperature. So the higher the temperature, the higher the average kinetic energy of the particles. Thermal energy is the total kinetic energy of all the particles. So as we increase the mass of an object, the temperature could be the same, but the thermal energy would change. So a glass of water could have the same temperature as a lake, but a lake is much bigger. It has many more water molecules, therefore it will have more thermal energy. Today we're going to be talking about systems and surroundings. So a system is what we focus our attention on. It could be the reactants and products of the reaction. It could be, a pot of water on the stove. It could be ice put into water in a glass. But it's where we're focusing our attention. The surroundings is everything else in the universe. So for example, if on a hot day you put ice cubes into a glass of water, that is going to be our system. When you pick up the glass and it feels cold, you are the surroundings. You're everything else around the system. Another example that we looked at, if we think back to our introductory to physical and chemical reactions that we did earlier in the year, we mixed together baking soda and vinegar inside of a Ziploc bag. And if you remember, hopefully the bag inflated with the creation of carbon dioxide. And I tried to have groups feel the liquid in the reaction, and it felt cold. So the system was the reactants inside of that bag, and then we were that surroundings. So when we look at our system and surroundings, we can look at the flow of heat, which is really just a form of energy. So heat is the energy transferred from an object at a higher temperature to an object at a lower temperature. Energy in the form of heat always flows from hot to cold. And when does the heat stop flowing? It stops flowing when we reach an equilibrium. So once the temperature of the system and the temperature of the surroundings are the same, heat will stop flowing. So again, going back to our ice water example, if you put the ice water in a glass and just leave it sitting on your table for long enough, that ice will melt. While the ice is melting, the drink will remain cold, but eventually all that ice will have melted, the phase change will be done, and slowly that glass of water will absorb the energy from the surroundings and the system will get warmer. Once the water's room temperature, that flow will stop, that flow of energy will stop, and you will see that room temperature and water temperature would be the same, that now energy would be evenly exchanged and would no longer flow. In our example of ice water and in the example I mentioned with baking soda and vinegar, we were looking at endothermic reactions. So in an endothermic reaction, if we think back to previous units, we looked at potential energy diagrams, and we saw diagrams that looked like these two pictures. We had our reactants in the beginning, we had our products at the end, and you would look at the difference between them. So our endothermic reaction is this one right here. And remember, in an endothermic reaction, In an endothermic reaction, the energy content of the products is higher. So the difference between the products and the reactants, that was our delta H, and it is positive. Heat will flow into the system from the surroundings. So when we mix together baking soda and vinegar, it felt cold. That was an endothermic reaction. It was absorbing the heat of our hands and the heat from the environment and thus felt cold. An exothermic reaction is this diagram here, where the energy contents in the reactants is higher. So we have all of this extra energy that must be released. So we're going to have a negative delta H, that we have extra energy that must leave the system. And that energy is going to be lost in the form of heat. So it will feel hot to us. And again, the energy that's gained by the surroundings is equal to the energy lost by the system. How do we calculate the energy lost or gained? These are some calculations we're going to look at. We'll keep it simple. Don't get too bogged down in them. I just wanted you all to see them. So heat of fusion and heat of vaporization, I'll talk a little bit more about on the next slide. And those are for our phase changes. Those are when we have the plateaus or these zero slope flat lines. Remember, that is an increase in potential energy. That is where we're getting a phase change. That's where we are breaking our intermolecular forces. So our heat of vaporization, heat of fusion. Heat of fusion is the energy that must be put into a solid in order to melt it. And again, melting is a phase change that is breaking intermolecular forces. Heat of vaporization is the energy that must be put into a liquid in order to vaporize it into a gas. And those values are going to be unique for different chemicals. Those values will be different for heat of fusion and heat of vaporization, even for the same chemical. Heat of vaporization is usually much higher. It takes a lot of energy to have a liquid boil. Energy can be reported in kilojoules, joules, or calories. Those are just units of energy. And those units of energy could be per mole or per gram. We're going to focus on per gram. Just be aware of your units if you're ever to do these calculations in the future. If I asked you for moles or grams, you'd have to do a one-step dimensional analysis fence beforehand. So we have two different formulas. We have Q equals MHF and Q equals MHV. Q is heat. So that is typically going to be in the unit of joules for us. M is for mass, and we're going to use grams. And then heat of fusion, heat of vaporization, those could be any of those units from the previous page: joules per gram, kilojoules per mole, joules per calorie per gram. We'll keep it simple. And these are typically numbers that are given to you that you would plug into an equation. Again, they are unique for every substance. So an example here is a data table with water, ethanol, and mercury. Specific heat we'll talk more about on a later slide, but heat of fusion and heat of vaporization are what I want us to focus on right now. So if I'm being asked for something to melt, I'm going to use a heat of vaporization number. And in this case, we're trying to melt ice, so that's our water. And there is our number here, 333.55 joules per gram. So because this is asking us to melt, we're using heat of fusion. So the equation that we're going to use is Q equals MHF, and we are solving for Q. So all we have to do is plug in the numbers we have. Mass is grams, that's 2.5. And then our HF is this 335.55 joules per gram. Grams will cancel. And we plug that into our calculator, and we get 834 joules. So with these problems, it's a very simple equation. It's just a matter of making sure your units are correct and that you're looking at the right substance and you're looking at fusion for melting, vaporization for boiling. One other example then, how much heat is transferred when 57 grams of mercury are vaporized? If you want to pause the video here and give it a try, go ahead. Okay, and we're back. Again, we're using this Q equals mHV. In this case, we're using HV because we are asked to vaporize something and we're being asked for mercury. So I'm going to use that 272 joules per gram. So 57 grams times 272 joules per gram. Again, grams will cancel. And we plug that into our calculator. And we get a big number, 15,500 joules. Why is this number so big? 57 grams is a lot. So the more mass we have, the more energy we will need. If you wanted to convert to kilojoules, just move that decimal place over 3. Not necessary, but Q often tends to be a very large number when we're talking about joules. So I just sometimes convert it to make it a little easier to see. Again, not necessary. But if you're someone who doesn't like those really big numbers, they're pretty easy to convert. But what about if there is a temperature change? So we are using heat of vaporization whenever we're at this top plateau. That's our HV. And we're using heat of fusion when we are at our phase change of solid to liquid. But what do we do in all these other spaces where we have our positive slope? This is where we have a temperature change. We're having an increase in kinetic energy. So we can't use the formulas we used before. Instead, we're going to use something called specific heat. So specific heat is the energy required to raise 1 gram of a substance 1 degree Celsius. So the more mass you have, the more energy it's going to take to heat something. Conductors have a low specific heat, and our metals fall into that category. If we think of copper wire, copper conducts heat and electricity. And the reason why it's a good conductor is because of this low specific heat. Conductors can easily transfer energy from one atom to another. And you've experienced this. If you have ever put a spoon either into hot soup and then burned your tongue on the hot spoon, if you've ever tried to scoop ice cream out of a container and you've used a metal spoon and it's frosted over really quickly and gotten cold very quickly, that is because metals are such good conductors with a low specific heat. In contrast, insulators have a high specific heat, so they require a lot of energy to change temperature. And water is our classic example of something having a high specific heat. If you think back to your biology days, that is something that was in your water unit and an important quality of water. It requires a lot of energy to change the temperature of an insulator. So if you have ever gone swimming, a pool, a lake, at the beginning of summer, that water is cold. It takes a long time to absorb the heat from the sun or a heater. And so the warmest time to go to the beach or a lake and go swimming is at the end of the summer. That's also why hurricane season doesn't really start until late August, September, and runs through November. The ocean has absorbed all of the heat of the sun over all of the summer months, gradually warming, and warm water is the source of energy for a hurricane. So there's a little background for you, but the main thing to take off of this is that insulators have a high specific heat. Water is a great example. Metals have a low specific heat, and those are your conductors. So again, specific heat energy required to raise 1 gram of a substance 1 degree Celsius. And the formula here is similar to what we had before. and it is Q equals MC delta T. Quick mad cat. And so that is heat is our Q. That is the heat or energy gained or lost. Again, that's typically going to be in joules. M is the mass of the substance. It's always just going to be in grams. We won't really deal with converting that at this time. C is the specific heat of a substance. That, again, is unique to the substance. Something like water has a big number. Something like copper has a small number. Do be careful because it's C, and then we also have temperature being degrees Celsius. It's a really similar abbreviation. Just be careful to keep them separate. And finally, delta T is the change in temperature. You don't have to worry about specific heat being positive or negative overall. It's about a transfer of heat from the system or the surroundings. So as long as you find the difference between the temperature, it's fine to just keep it as a positive value overall. And for example, the C of water is 4.184 joules per gram degrees Celsius. That is also known as a calorie when we look into units. This 4.184 is a pretty large number. So it takes 4.184 joules to change 1 gram of water 1 degree Celsius. This does have a really weird unit for specific heat, but when we do some sample calculations, you'll see that everything cancels out. So an example, solid magnesium has a specific heat of 1.01 joules per gram Celsius. How much heat is given off by a 20-gram sample when it cools from 70 to 50 degrees Celsius? So our equation, Q equals MC delta T, we are solving for Q. We're being asked to solve for energy. Any example you ever do with specific heat, just know it's an algebra example. You will be given 3 of the 4 variables and you just need to find the missing one. So in this case, we are just solving for Q. We have been given grams, we have been given the specific heat, and we know that it cools from 70 to 50 degrees. I can simplify this a little bit more. That we have 20 grams times the specific heat of magnesium, and the change in temperature was 20 degrees Celsius. It is fine for you to do that separately or just write that number down, but it is the difference in temperature. And then we can see that grams will cancel, degrees Celsius will cancel, and the unit that we're left with is joules. Put that in your calculator, 20 times 1.01 times 20, 404 joules. Another example, specific heat of aluminum, 0.9 joules per gram Celsius. How much heat is required to raise the temperature of 55 grams by 10 degrees Celsius? So again, we're being asked to solve for Q. We have been given M, we have been given C, and we've been given the change in temperature, delta T. So we just plug each of those numbers in. 55 times 0.9 times 10. Cancel all those units out and multiply, and we get 495 joules. Okay, and one final example. A 12-ounce can of soda weighs 456 grams. How many joules are released when a can of soda is cooled from 25 degrees Celsius to 4 degrees? Here we can see we have a mass. We have temperature change that we can solve for. But what is the specific heat? Well, in this case, we know that soda is mostly water, so I'm just going to use the number for water. All right, I'm going to pause here again and let you try this problem. Okay, and the answer I got was 40,100 joules, which is a lot of energy. I converted to kilojoules just to make it a slightly prettier number. Again, not necessary. Hopefully you got that same number I did. All right, folks, that is all we have for this week. Thanks for tuning in and have a great day.